The first object to have been reported by astronomers that came from outside the solar system looked really weird. It was discovered by a telescope in Hawaii.
In October 2017, a faint, fast-moving object streaked across the Hawaiian sky, and with it began one of the most perplexing cosmic mysteries of our time. Dubbed ʻOumuamua, meaning scout or messenger in Hawaiian, the object defied every expectation astronomers held about interstellar visitors. It accelerated unnaturally as it exited the solar system, but emitted no tail, no gas, no dust, none of the telltale signs of a comet. For 6 years, scientists have debated its origin, composition, and trajectory, unable to neatly fit it into any known category of celestial object. Now, astronomers have finally found, or so they say, the possible origin of Oumuamua, and they are gravely concerned. Let's walk through this story from the very beginning. Tracing the origins. Advanced astrophysical modeling. When Oumuamua silently swept through our solar system in October 2017, no one saw it coming. It was already speeding away from the sun when astronomers first detected it. There had never been any confirmed interstellar visitor before. Nothing from outside the solar system had ever been tracked so closely, and so no telescope had been watching for such an arrival. The night sky appeared as calm and predictable as ever, dotted with familiar stars and planets, offering no warning that something utterly foreign had slipped through. Traveling at nearly 315,000 kilometers per hour, Oumuamua was already on its way out, allowing just 11 days of high-quality observation before it faded beyond reach. This object from another star system had passed so close without notice. Naturally, in the years since, scientists have raced to trace the object's origins, hoping that its past trajectory might offer clues about its nature. A significant breakthrough came in 2018 when Harvard astronomer Avi Loeb collaborated with astrophysics student Shmuel Bialy to investigate the object's motion using advanced modeling techniques. Their analysis was among the first to seriously question the natural explanations for Oumuamua's behavior and led to the development of increasingly sophisticated methods to map its possible path through the galaxy. At the heart of this effort was the incorporation of precise astrometric data from the European Space Agency's Gaia mission, which provided an unprecedented map of the positions, motions, and velocities of over 1 billion stars in the Milky Way. Gaia's data, released as part of Data Release 2, or DR2, in April 2018, revolutionized how astronomers approach questions of celestial motion and stellar origins. The team used these data to model not only the trajectory of Oumuamua, but also the gravitational field of the Milky Way itself, which is essential when calculating the past movements of interstellar objects. This involved complex numerical integration, where small changes in position, velocity, and gravitational influence were calculated over time to rewind the path of Oumuamua with as much precision as possible. The goal was to determine whether the object could be matched to any nearby star system from which it may have been ejected. The results of this modeling were both illuminating and puzzling. Loeb and Bialy's simulations traced Oumuamua's origin to a region in the thin galactic disk, a component of the Milky Way that contains young stars, gas, and dust, typically less than a few billion years old. The simulations suggested that the object may have originated from a low-mass, relatively young stellar system. These stars are usually not more than 1 to 2 billion years old and are often M-dwarfs or other low-luminosity bodies that lack massive gravitational fields or dynamic stellar interactions. This proposed point of origin introduced a major astrophysical paradox. In galactic dynamics, ejecting a large object like Oumuamua from a star system into interstellar space at high velocity requires powerful gravitational interactions, typically involving either a massive planet, a stellar binary, or a close encounter with another star. Low-mass stars in the thin disk, by contrast, are gravitationally weak and relatively isolated, making them unlikely candidates to eject rocky bodies with speeds exceeding 26 kilometers per second, which was the velocity at which Oumuamua entered our solar system. According to Loeb and Bialy, if the object originated from a region where no known mechanism could feasibly account for such ejection speeds, then either our understanding of those regions is incomplete, or Oumuamua is not a product of natural ejection at all. Further complicating the picture, the object's extremely low vertical oscillation relative to the galactic plane, the slight bobbing up and down expected from most interstellar bodies, suggested that it had not been traveling for billions of years. In fact, its motion was unusually well aligned with the motion of the local standard of rest, the average motion of stars in the vicinity of the Sun. This hinted that it may have only recently entered interstellar space, perhaps within the last few 100 million years. Given that our Sun is approximately 4.6 billion years old, and most ejected comets and asteroids from mature systems are weathered by cosmic radiation and collisions, Oumuamua's unblemished, smooth surface and its origin from a young stellar environment were both striking anomalies. While mainstream astronomers continue to explore natural explanations, Loeb and Bialy's modeling effort is one of the most comprehensive attempts to place Oumuamua within a galactic context. So, what do we know so far? Peculiar motion and other anomalies. When Oumuamua was first detected on October 19, 2017 by the Pan-STARRS-1 telescope in Hawaii, astronomers were quick to notice its extraordinary behavior. Officially designated 1I/2017 U1, it became the first confirmed interstellar object observed passing through our solar system. As more data was gathered, it became clear that Oumuamua was unlike any comet or asteroid previously recorded. Among its many oddities, perhaps the most striking was its peculiar motion. Observations revealed that it was not simply rotating in a uniform way, but rather exhibiting a complex, tumbling motion, wobbling like a top. This led to the hypothesis that it might be shaped more like a pancake than a cigar, contrary to initial assumptions. In 2021, further analysis of its motion was enriched by stellar data from the European Space Agency's Gaia mission, Gaia DR2, and subsequent datasets allowed astronomers to trace Oumuamua's inbound trajectory more precisely and identify candidate home stars. The most notable finding from this effort was that the stars in the direction Oumuamua likely came from were all small, long-lived dwarf stars. These stars exhibited low levels of magnetic activity, minimal ultraviolet output, and lacked large planetary systems that could have provided a gravitational slingshot to eject a body at interstellar speeds. This lack of any discernible slingshot mechanism in the vicinity made Oumuamua's high entry velocity of approximately 26.3 kilometers per second relative to the Sun even more baffling. If no gravitational interaction flung it out, how did it reach such speeds? Even more puzzling was Oumuamua's galactic trajectory. Astronomers studying its orbital elements noticed that its path was extremely flat. It traveled in an unusually planar orbit, closely aligned with the Milky Way's midplane, which is the thin, dense disk where most stars in our galaxy lie. Natural interstellar objects, like most stars and matter expelled by supernovae, generally follow more randomly inclined orbits due to dynamic perturbations over millions of years. In contrast, Oumuamua's razor-thin galactic alignment seemed statistically anomalous. Harvard astronomer Avi Loeb pointed out that the odds of a random interstellar object having such a flat trajectory by chance were less than 1 in 500. But wait, there's more. Loeb has also proposed that the object's positioning could be intentional if the object were artificial. He asserts that the solar system, like every other planetary system, moves through the galaxy, and encountering an object in the LSR would be exceedingly rare, unless it were positioned there deliberately. Moreover, on October 14, 2017, just 5 days before its detection, Oumuamua made its closest pass to Earth, flying within approximately 24 million kilometers or 15 million miles. This is about 60 times the Earth-Moon distance. This flyby distance is significant not just because of its relative nearness, but because the object's path placed Earth almost precisely at the point of closest solar approach. This scenario is highly unlikely under random conditions. To evaluate just how improbable this was, astronomers have run thousands of computer simulations modeling hypothetical interstellar objects entering the solar system from various angles and velocities. These simulations take into account gravitational influences from the Sun and planets, the distribution of incoming trajectories in three-dimensional space, and the sheer randomness of encounters on cosmic timescales. The results from a study led by astrophysicists at institutions including the Harvard-Smithsonian Center for astrophysics showed that, under normal circumstances, there is less than a 1% probability that a natural interstellar object would follow a trajectory leading to such a near-Earth pass, especially so soon after entering the solar system. Most modeled trajectories result in flybys of the Sun, Mercury, or Venus, with significantly fewer close approaches to Earth or Mars. So, was this flyby a coincidence, or could it suggest something more deliberate? Avi Loeb has postulated that such precision hinted at the possibility of Oumuamua being a probe or reconnaissance object. In Loeb's words, nature doesn't line up targets this precisely without help. If Oumuamua's flyby was not a random fluke, what might that imply? One speculative but technically grounded hypothesis is that of a targeting or information-gathering mission. In principle, an advanced extraterrestrial civilization, using artificial probes or light sails, could deploy devices on long-term voyages to monitor habitable systems like our own. Such probes might be programmed to coast inertially for millennia and activate upon encountering signs of life, such as radio signals, atmospheric biomarkers, or other techno-signatures. Oumuamua's silent, fast flyby near Earth in such a precise corridor fits at least the basic outline of a passive reconnaissance strategy, although no direct evidence, such as radio transmissions, optical beacons, or sudden course corrections, was observed. Now, we can move on and ask an even more puzzling question. How did Oumuamua accelerate? The sail-like theory. Oumuamua's most confounding characteristic, beyond its interstellar origin, tumbling motion, and unusual trajectory, was its subtle but measurable acceleration away from the Sun that could not be explained by gravity alone. After it passed perihelion, which is the point in an object's orbit where it is closest to the Sun, on September 9, 2017, astronomers tracking its course noticed that Oumuamua's velocity increased slightly as it exited the inner solar system. In this way, it mimicked the behavior of comets, which often gain speed due to jets of gas expelled by sublimating ices. However, Oumuamua exhibited none of the classic signs of cometary activity: no visible tail, no coma, and no detectable gas or dust emission. This contradiction put it at odds with all known natural celestial bodies that undergo similar changes in velocity. In June 2018, a study published in Nature by Marco Micheli and colleagues confirmed the non-gravitational acceleration of Oumuamua with high confidence. Using observations from telescopes such as the Canada-France-Hawaii telescope and the Very Large Telescope in Chile, the researchers demonstrated that the object's motion deviated from a purely gravitational trajectory by a small but consistent amount. This observational gap led Harvard astrophysicist Avi Loeb and postdoctoral fellow Shmuel Bayali to propose a radically different hypothesis in a November 2018 paper published in the Astrophysical Journal Letters, that Oumuamua might be a light sail, an ultra-thin, engineered object designed to harness solar radiation pressure as a means of propulsion. Solar radiation pressure is the force exerted by photons from the Sun. While minute, this force is enough to push extremely thin objects over time, an idea that has been explored in modern space technology. For the light sail theory to hold, Loeb and Bialy calculated that Oumuamua would need to be no more than 0.3 to 0.9 millimeters thick and several hundred meters wide, approximately 400 meters in diameter, to maintain the observed acceleration without disintegrating under the stresses of space travel. Such dimensions would result in a very high area-to-mass ratio, making the object extremely responsive to solar radiation but undetectable to infrared telescopes like NASA's Spitzer, which failed to register any heat signature from Oumuamua during its exit phase. The lack of thermal emission was consistent with a very thin, non-reflective, and possibly highly porous structure. The concept of a light sail is not speculative in human engineering. The Japan Aerospace Exploration Agency launched Ikaros in 2010, the world's first interplanetary solar sail spacecraft. It successfully demonstrated propulsion by sunlight alone, using a sail 20 meters across and just 7.5 microns thick. More recently, the Planetary Society launched Light Sail 2 in 2019, which deployed a 32-square-meter reflective sail in Earth orbit and successfully raised its orbit using solar radiation. These missions have proven that solar sailing is not only possible, but a viable method of propulsion for long-term, fuel-free travel, though still in its infancy. If Oumuamua were indeed a light sail, it would imply the existence of a civilization with technological capabilities far beyond Earth's current stage, capable of building extremely thin, large-scale, resilient materials that can survive interstellar conditions for potentially millions of years. Loeb suggested it could be a fragment of a larger structure, perhaps a discarded component of an alien probe, a derelict light sail drifting through space, or even a functioning reconnaissance object. Moreover, despite being an interstellar object, Oumuamua is estimated to be just 1 to 2 billion years old. This is surprisingly young compared to the Sun or Earth. However, if it came from a star system only 1 to 2 billion years old, it would imply life evolved and developed advanced spacefaring technology far faster than it did on Earth. To reconcile this, Loeb and others have proposed that the object may not have originated in that young star system at all. Instead, it could be a relic from a much older civilization that used the system as a transit point or outpost. This theory aligns with the concept of von Neumann probes, or self-replicating machines capable of spreading across the galaxy, operating independently of their origin civilizations. However, skepticism remains strong. Alternative explanations have included hydrogen icebergs, nitrogen-rich exo-Pluto fragments, and dust-driven acceleration, but none fully explain the absence of emission, the precise acceleration profile, or Oumuamua's shape and mass constraints. Critics also point out the lack of follow-up observations due to the object's speed and late discovery. Nonetheless, Oumuamua's unexplained acceleration is a compelling mystery. Oumuamua may not be alone. In 2014, an object later catalogued as CNEOS 2014-0108, or IM1, entered Earth's atmosphere near Papua New Guinea. Initially unremarkable, its status changed after Harvard astrophysicists Amir Siraj and Avi Loeb re-examined data in 2019, using figures released by the US Department of Defense. They found that IM1 had been traveling faster than 60 kilometers per second relative to the Sun before entering the atmosphere, exceeding the solar system's escape velocity. In 2022, the US Space Command confirmed its interstellar origin, officially making IM1 the first known interstellar object to reach Earth, predating Oumuamua by 3 years. What made IM1 even more unusual was its extreme strength. It survived atmospheric pressures that destroy most meteors, exploding with the energy of 110 kilotons, and suggesting a structure over 10 times tougher than iron meteorites. This resilience prompted speculation about IM1's composition and origin. Loeb and Siraj suggested it could consist of material unknown in our solar system, potentially even engineered. This reframed the conversation initiated by Oumuamua in 2017. If 2 confirmed interstellar objects were detected within a few years, such encounters might not be rare. This gave rise to theories that some of these objects could be directed rather than random, raising the possibility that Earth is being visited, or at least intersected, by interstellar probes. To investigate further, Loeb launched the Galileo project at Harvard in 2021. This initiative focuses on collecting high-quality data on unidentified aerial and space phenomena using AI-powered sensors and tracking systems optimized for fast-moving local objects. In 2023, a Galileo-led expedition to the ocean floor near Manus Island recovered metallic spherules, likely tied to IM1's disintegration. Preliminary analysis suggests they may not match known solar system materials. Loeb argues this growing body of data could indicate that we are already encountering remnants or messengers of advanced civilizations. Similarly, Comet 2I Borisov, discovered by amateur astronomer Gennady Borisov on August 30, 2019, provided astronomers with a textbook example of a natural interstellar comet. Unlike Oumuamua, which exhibited no visible coma or tail, Borisov displayed classic cometary activity, a developing coma and dust tail captured by major observatories, including Hubble, and Gemini. Its interstellar status was quickly confirmed by its hyperbolic trajectory and excess velocity of 32 kilometers per second. However, Borisov closely matched the characteristics of comets from our own solar system. Observations further confirmed this natural origin, showing high carbon monoxide levels and other familiar molecules, pointing to formation in a cold, distant region of a protoplanetary disk. In stark contrast, Oumuamua lacked all signs of volatile activity, despite displaying non-gravitational acceleration as though it were being pushed by solar radiation. Its thin, pancake-like shape and unusual trajectory prompted Avi Loeb and Shmuel Bayerly to hypothesize it might be a light sail of artificial origin. So, what do we get when we put all of this data together? Well, some experts have proposed the silent probe theory to connect the dots. This theory posits that despite emitting no detectable radio signals across commonly monitored frequencies, Oumuamua might still be an artificial object designed to operate in stealth or dormancy. Extensive scans by SETI and Breakthrough detected no transmissions. Yet theorists like Avi Loeb suggest it could be silently ferrying data, acting as a passive interstellar probe, much like a cosmic USB stick. He is convinced that its anomalous behavior, lack of emissions, and unusual trajectory hint at deliberate design rather than random natural origin. The absence of signals might reflect sophisticated engineering, choosing passive observation, energy-efficient drift, or phase change memory to withstand millennia in deep space. With Oumuamua now beyond reach and headed out of the solar system, its silence paradoxically intensifies its mystery. Will future interstellar visitors clarify this enigma? Only time will tell. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.